back to the small, where we begin our climb up the ladder of structure. This is how we represent an electron visually. The particle itself is a fundamental particle and is too small to be seen by any imaginable instrument of observation. So we instead represent the properties that allow the electron to interact. The central small dot represents the weak charge of the electron. This charge, entirely separate from electric charge, gives rise to the weak nuclear force. This force causes radioactive decay, and its typical range is much smaller than the diameter of a proton. The larger volume of shifting purple is meant to represent the electric charge of the electron. This charge is the generator of the electromagnetic force, which has infinite range, although the drop-off of strength is pretty dramatic as we move away from the electron. The electromagnetic force is how electrons interact with other electrically charged particles and with magnetic fields. These interactions make the structure of atoms and molecules possible. This gives rise to almost all of the complexity that we see around us. This is our depiction of a proton. It is composed of 2 up quarks and 1 down quark, as you can see from the tiny rings of color near the center of the quark. The overall charge of a proton is positive, and so we have given it a gold shell. Note that we can simply add the charges of the individual quarks to get the charge of a proton. Oh, protons taste sour, like vinegar and lemonade. This is our depiction of a neutron. It is composed of 2 down quarks and 1 up quark, as you can see from the tiny rings of color near the center of the quark. The overall charge of a neutron is neutral, so we have given it a silver shell. Note that we can simply add the charges of the individual quarks to give the charge of the neutron. The red, green, and blue colors of the quarks represent the color charge which generates the strong nuclear force that holds them together. It comes in 3 different charges, represented here by 3 colors, and for different colors, the force is attractive. The mediator of the strong force, the particle that is exchanged in an interaction, is a gluon. We represent gluon exchange as the occasional wispy string between the quarks. As you can see, the gluons have color themselves, and each gluon exchange causes the quark involved to swap color. Although we show quark motion inside of the neutron as leisurely, they are actually traveling close to the speed of light. There are 2 kinds of quarks that are found in normal matter. Physicists call them flavors of quarks. These quarks are the up quark and the down quark. A proton is formed from 2 up quarks and 1 down quark, while its slightly heavier cousin, the neutron, is formed from 2 down quarks and 1 up quark. The red, green, and blue colors of the quarks represent a property that attracts them to one another. It is this color charge property of the quarks that hold them together in a proton or a neutron. These protons and neutrons can then combine to form the nucleus of each element in the periodic table. 1 proton in the nucleus makes hydrogen. 2 form helium. 6 carbon. 8 oxygen. 79 is gold. And 92 uranium. Neutrons help hold the protons together. Because of their electric charge, protons would repel each other more strongly if neutrons were not present, and the heavier elements would come apart. There are approximately as many neutrons in each element as there are protons. Atoms are formed when the positively charged protons in the nucleus capture the negative electrons. Neutral atoms capture one negative electron for each positive proton in the nucleus. So, hydrogen has one electron to go with its one proton. Helium, 2 electrons. Carbon has 6. Oxygen, 8. Gold has 79. And uranium, 92. There are nearly 90 stable elements. The largest of them contain close to 800 fundamental particles joined in a complex but stable structure. But electrons cannot just gather around in a crowd. Once again, the strange, wonderful world of the tiny has its idiosyncrasies. Electrons arrange themselves in shells inside an atom like the layers of an onion. And only 2 electrons can fit per layer. So the more electrons an atom has, the further away from the nucleus the outer shells must be. And that means these electrons are more loosely held. It is this difference in how tightly electrons are held in each different kind of atom that determines the chemical properties of the element. This accounts for the ability of metals to conduct electricity, the aloofness of noble gases, and the formation of molecules. It turns out that protons in 2 or more different nuclei can sometimes capture and fight over the same electron. And when that happens, atoms of different elements are joined together to form molecules. This oxygen molecule is sharing 2 of its electrons with 2 hydrogen atoms. This is how a water molecule is formed.